Caesium-137, Caesium-137, 13,755 Cs, or radiocesium, is a radioactive isotope of cesium that is formed as one of the more common fission products by the nuclear fission of uranium-235 and other fissionable isotopes in nuclear reactors and nuclear weapons. Trace quantities also originate from natural fission of uranium-238. It is among the most problematic of the short to medium lifetime fission products. 137 Cs has a relatively low boiling point 671 deg C, 1240 F, and is volatilized easily when released suddenly at high temperature, as in the case of the Chernobyl nuclear accident and with atomic explosions, and can travel very long distances in the air. After being deposited onto the soil as radioactive fallout, it moves and spreads easily in the environment because of the high water solubility of cesium's most common chemical compounds, which are salts. 137 Cs was discovered by Glenn T. Seaborg and Margaret Melhase. Decay Cesium-137 has a half-life of about 30.17 years. About 94.6% decays by beta emission to a metastable nuclear isomer of barium, barium-137 Ba, Ba-137. The remainder directly populates the ground state of barium-137, which is stable. Metastable barium has a half-life of about 153 seconds and is responsible for all of the gamma-ray emissions in samples of cesium-137. 137 Ba decays to the ground state by emission of photons having energy 0.6617 MeV. A total of 85.1% of 137 Cs decays lead to gamma-ray emission in this way. 1 gram of Cc-137 has an activity of 3.215 terabecquerel TBq. Uses. Cesium-137 has a number of practical uses. In small amounts, it is used to calibrate radiation detection equipment. In medicine, it is used in radiation therapy. In industry, it is used in flow meters, thickness gauges, moisture density gauges, for density readings, with a Mirac-241/beryllium providing the moisture reading, and in gamma-ray well logging devices. Cesium-137 is not widely used for industrial radiography because it is hard to obtain a very high specific activity material with a well-defined and small shape as cesium from used nuclear fuel. Also, the higher specific activity cesium sources tend to be made from very soluble cesium chloride CsCl. As a result, if a radiography source was damaged, it would increase the spread of the contamination. It is possible to make water-insoluble cesium sources with various ferrocyanide compounds, such as NiTWO-FeCN6 and ammonium ferric hexacyanoferric F. A large emitting volume will harm the image quality in radiography. Iridium-192 and cobalt-60, 6027 Co are preferred for radiography, since these are chemically non-reactive metals and can be obtained with much higher specific activities by the activation of stable cobalt or iridium in high-flux reactors. As an almost purely man-made isotope, Cesium-137 has been used to date wine and detect counterfeits, and as a relative dating material for assessing the age of sedimentation occurring after 1945. Cesium-137 is also used as a radioactive tracer in geologic research to measure soil erosion and deposition. Health risk of radioactive cesium. Cesium-137 reacts with water, producing a water-soluble compound cesium hydroxide. The biological behavior of cesium is similar to that of potassium and rubidium. After entering the body, cesium gets more or less uniformly distributed throughout the body, with the highest concentrations in soft tissue. 114. The biological half-life of cesium is about 70 days. A 1961 experiment showed that mice dosed with 21.5 mSci/G had a 50% fatality within 30 days, implying an LD50 of 245 mg/kg. A similar experiment in 1972 showed that when dogs are subjected to a whole-body burden of 3,800 mSci/kg, 140 mbq/kg, or approximately 44 mg/kg of Caesium-137 and 950 to 1,400 rads, they die within 33 days. Important researches have shown a remarkable concentration of 137 CS in the exocrine cells of the pancreas, which are those most affected by cancer. In 2003, in autopsies performed on 6 children dead in the polluted area near Chernobyl, where they also reported a higher incidence of pancreatic tumors, Bandajewski found a concentration of 137 CS 40-45 times higher than in their liver, thus demonstrating that pancreatic tissue, accidental ingestion of Caesium-137, can be treated with Prussian blue Phi III for Phi IAC-N63, which binds to it chemically and reduces the biological half-life to 30 days. Radioactive cesium in the environment. Caesium-137, along with other radioactive isotopes Cesium-134, iodine-131, xenon-133, and strontium-90, were released into the environment during nearly all nuclear weapon tests and some nuclear accidents, most notably the Chernobyl disaster and the Fukushima. Caesium-137 in the environment is substantially anthropogenic, human-made. Caesium-137 is produced from the nuclear fission of plutonium and uranium and decays into barium-137. Before the construction of the first artificial nuclear reactor in late 1942, the Chicago Pile-1, Cesium-137 had not occurred on Earth in significant amounts for about 1.7 billion years. By observing the characteristic gamma rays emitted by this isotope, one can determine whether the contents of a given sealed container were made before or after the first atomic bomb explosion Trinity Test, 16 July 1945, which spread some of it into the atmosphere, quickly distributing trace amounts of it around the globe. This procedure has been used by researchers to check the authenticity of certain rare wines, most notably the purported Jefferson bottles. Surface soils and sediments are also dated by measuring the activity of 137 CS. Chernobyl disaster. As of today, and for the next few hundred years or so, Caesium-137 and strontium-90 continue to be the principal source of radiation. The mean contamination of Caesium-137 in Germany following the Chernobyl disaster was 2,000 to 4,000 Bq/m2. This corresponds to a contamination of 1 mg/km2 of Caesium-137, totaling about 500 grams deposited over all of Germany. In Scandinavia, some reindeer and sheep exceeded the Norwegian legal limit 3,000 Bq/kg 26 years after Chernobyl. As of 2016, the Chernobyl Caesium-137 has decayed by half, but could have been locally concentrated by much larger factors. Fukushima Daiichi disaster. Incidents and accidents. Caesium-137 gamma sources have been involved in several radiological accidents and incidents. 1987 Goiânia, Goiás, Brazil. In the Goiânia accident of 1987, an improperly disposed of radiation therapy system from an abandoned clinic in Goiânia, Brazil, was removed, then cracked. This led to 4 confirmed deaths and several serious injuries from radiation contamination. Cesium gamma ray sources that have been encased in metallic housings can be mixed in with scrap metal on its way to smelters, resulting in production of steel contaminated with radioactivity. 1989 Kramatorsk, Donetsk, Ukraine, Ukraine, Donetsk, Ukraine, 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 Ukraine. The Kramatorsk radiological accident happened in 1989 when a small capsule containing highly radioactive Cesium-137 was found inside the concrete wall of an apartment building in Kram. It is believed that the capsule, originally a part of a measurement device, was lost in the late 1970s and ended up mixed with gravel used to construct the building in 1980. Over 9 years, 2 families had lived in the apartment. By the time the capsule was discovered, 6 residents of the building had died from leukemia and 17 more had received varying doses of radiation. 1997, Georgia. Seven Georges. In 1997, several Georgian soldiers suffered radiation poisoning and burns. They were eventually traced back to training sources abandoned, forgotten, and unlabeled after the dissolution of the Soviet Union. One was a Cesium-137 pellet in a pocket of a shared jacket that put out about 130,000 times the level of background radiation at 1 meter distance. 1998, Los Barrios, Cadiz, Spain. In the Acerinox accident of 1998, the Spanish recycling company Acerinox accidentally melted down a mass of radioactive Cesium-137 that came from a gamma-ray generator. 2009 Tongchuan, Shaanxi, China. In 2009, a Chinese cement company in Tongchuan, Shaanxi province was demolishing an old, unused cement plant and did not follow standards for handling radioactive materials. This caused some Cesium-137 from a measuring instrument to be included with 8 truckloads of scrap metal on its way to a steel mill, where the radioactive cesium was melted down into the steel. March 2015, University of Tromsø, Norway. In March 2015, the Norwegian University of Tromsø lost 8 radioactive samples, including samples of Cesium-137, Americium-241, and Strontium-90. The samples were moved out of a secure location to be used for education. When the samples were supposed to be returned, the university was unable to find them. As of 4 November 2015, the samples are still missing. March 2016, Helsinki, Uusimaa, Finland. On 3 and 4 March 2016, unusually high levels of Cesium-137 were detected in the air in Helsinki, Finland. According to Stuck, the country's nuclear regulator, measurements showed 4,000 mbq/m3, about 1,000 times the usual level. An investigation by the agency traced the source to a building from which Stuck and a radioactive waste treatment company operate. May 2019, Seattle, Washington, US. 13 people were exposed to Cesium-137 in May 2019 at the Research and Training Building in the Harborview Medical Center complex. A contract crew was transferring the cesium from the lab to a truck when the powder was spilled. 5 people were decontaminated and released, but 8 who were more directly exposed were taken to the hospital while the research building was evacuated.